Okay, so today we're doing Le Chatelier's principle. This is the first part of inquiry question 2. Our syllabus outcome is investigate the effects of temperature, concentration, volume, and or pressure on a system at equilibrium. Explain how Le Chatelier's principle can be used to predict such effects. For example, heating cobalt chloride hexahydrate, interaction between nitrogen dioxide and dinitrogen tetroxide, uh, iron thiocyanate, and varying concentrations of ions. So, let's do the revision bit first. Cast your mind back to the last lesson. Have a go at the questions. Um, and if you've done the questions, I'm going to do the answers now. So, the equilibrium of a system is largely controlled by thermodynamic factors. Both the forward and reverse reactions have the same activation energy, and the reactants and products may have different total energy, leading to one of the reactions being favored, so either the forward or the reverse. Now, Le Chatelier's principle. The principle is named after French chemist Henri-Louis Le Chatelier, and it can be stated as when a simple system in thermodynamic equilibrium is subjected to a change in concentration, temperature, volume, or pressure, the system changes to a new equilibrium, and this change partly counteracts the applied change. That is to say, that's the fancy way of saying if a chemical system in equilibrium is altered, then the equilibrium will shift in such a way as to minimize the change. Okay, so basically, whatever we do to it, it wants to do the opposite. Our equilibrium is like a petulant child. It really doesn't do what you say, like what you want it to do. It does the opposite, always the opposite. So let's have a look at changes. So as stated in Le Chatelier's principle, there are four main ways that a chemical equilibrium system can be disturbed. We can change the concentration of a single reagent, so we can add something, we can subtract something. We can change the temperature of the system, because remember, it's a closed system, so energy can go in or out. We can change the pressure, so we can basically reducing the volume, increasing the pressure of gaseous equilibrium systems. And we can change the volume. So it's akin to changing pressure. Just remember that as we decrease volume, we increase pressure and vice versa. So those last two are going to be kind of covered in the same point. So changing concentration. What happens when we change concentration? So the concentration of reagents can be changed by adding or removing it from the reaction. So you could have an equilibrium system where um, you can add some extra protons or something, whatever whatever chemicals are in the system. So we can add some or we can take some away. If a chemical is added, then the equilibrium will shift towards the side that doesn't contain that chemical. So it shifts away from the side of the stuff we add. Okay, we'll do some actual examples shortly. Like this one. So we've got 2 sulfur dioxide plus oxygen is in equilibrium with 2 sulfur trioxide. Now, if we add SO2 to the system, okay, so we're adding stuff here. If we do that, the equilibrium is going to shift away from that side, so it's going to shift that way towards the products. So it's going to minimize that change. So if we add 5 moles, it might use up 4 moles. So, for example, it might be something like that. If we add O2 to the system, it's also going to shift towards the products because it's the opposite side of where we've added stuff. If we add SO3, it's actually going to go the opposite way. So we've added stuff to the right-hand side, so it's going over to the left. Here, again, Haber process. 3 hydrogens plus nitrogen is in equilibrium with 2 ammonia. If we remove NH3, so we've taken some NH3 and we've buggered it off, what's going to happen is the system will move towards that side. Okay, so if we remove ammonia, it's going to shift towards the products. Okay. If hydrogen is removed, so let's say we take some hydrogen just out of the system, okay, if we've removed it, then the equilibrium is going to shift towards that side. So ammonia is going to get used up. It's going to produce some more hydrogen, some more nitrogen. Same with nitrogen. If our nitrogen is removed, okay, we're removing stuff from the left side, so the equilibrium is going to shift towards that side. So it's going to make some more nitrogen, and it's going to use up some of that ammonia to do it. Now, changing pressure and volume. So if the pressure inside a reaction vessel is increased, then the concentrations of all the reagents will increase. Now, if this happens, then the system moves to the side containing the least number of moles. Conversely, a decrease in pressure will push the equilibrium to the side with more moles. Change in volume is similar, so if we reduce the volume, we're increasing the pressure. So it's the same thing. So reducing the volume increases the pressure, which means it moves to the side containing the lower number of moles. And this all relates to the ideal gas law and how the number of moles is proportional to pressure times volume at a given temperature. So let's have a look at this example again. So this is our sulfur dioxide plus oxygen gives us sulfur trioxide. In this reaction, there are 3 moles of reactants. So 1, 2, 3. So that's 3 moles. And on our product side, there's 2 moles. Okay. Basically, if we increase the pressure, so pressure goes up, it's going to move to the side with lower number of moles, so it's going to move towards the products. Okay. If the pressure is decreased, the equilibrium will shift to the reactants as there are more moles on that side. So if we've lowered the pressure, it's going to shift that way to try and increase the pressure. Okay. Now remember, this is because our ideal gases take up a certain volume per mole. Okay, it was like 24 odd liters at 25 degrees. The actual number's on your formula sheet, so you can look it up. Yeah, so for this reaction, you'd expect to have, you know, 48 liters on the right-hand side, but 72 liters on the left-hand side. Okay, so there's that difference in volume. So it also changes pressure. Now let's have a look at ammonia again. So the Haber process, on the left-hand side, we have 4 moles of reagents, and on the product side, we have 2 moles. So if the pressure is increased, it'll move towards the products because we have less number of moles on the side of the products. If the pressure is decreased, the equilibrium will shift to the reactant side as there's more moles on that side. So it tries to minimize that change. Now, changing temperature. When a reaction occurs, there is always an associated change in enthalpy. Now, if the enthalpy is negative, heat will be released to the environment. And if it's endothermic, heat will be taken from the environment. So remember, it's all about that changing chemical potential energy and how it's either given or taken away from the surroundings in the form of kinetic energy. Now, knowing this, we can predict how a reaction will go based on if it's endo or exothermic. Basically, here we've got the Haber process again. It has a negative delta H, so it's exothermic going towards the products. So the reaction is exothermic, meaning that the forward reaction will cause the surroundings to heat up, and the reverse reaction will cause the surroundings to cool down. So if we increase the temperature of the reaction vessel, the equilibrium will move to the side of the reactants trying to cool it down. So we add some heat in, it wants to remove that heat, so it'll go the endothermic pathway. And so it's exothermic in the forward reaction, so it's endothermic in the reverse. And so if we add heat, it's going to want to go towards the endothermic side, so it's going to go towards the reactants. If we decrease the temperature, the opposite thing happens. We decrease the temperature, so it wants to increase it, and do that by moving towards the exothermic side. So if we cool it down, it will minimize the change by going towards the, doing the exothermic reaction and going towards the products. Okay. Here we've got another example. Oxygen plus nitrogen is in equilibrium with 2 NO, so nitrogen monoxide. The delta H here is positive, so it means it's endothermic. So let's go endothermic in the forward reaction, exothermic in the reverse reaction. So the reaction is endothermic, meaning that the forward reaction will cause the surroundings to cool down, and the backwards reaction will cause the surroundings to heat up. If we increase the temperature of the reaction vessel, the equilibrium will move to the side of the products trying to cool it down. So because it's endothermic in the forward reaction, basically the forward reaction is going to occur if we heat it up. Now, if we cool it down, it'll want to go the exothermic way, so it'll go towards the reactants, producing more heat, trying to minimize that change. So here's a mini summary. So before we kind of put all of this together into some examples, this is what we've covered so far. So equilibrium systems will always move to minimize any change. If you add a chemical, it will move away from that side. So it'll move, like if you add to the left, it'll move towards the right. If you add to the right, it will move towards the left. If you increase the pressure, it'll move to the side with the least number of moles to try and reduce the pressure. And if you increase the temperature, it will move towards the side that cools down, so the endothermic side. Now, all of these things happen both ways. So if we decrease the pressure, it'll move to the side with more moles. And if we decrease the temperature, it will move to the side that warms it up. So let's have a look. Here we've got oxygen plus carbon is in equilibrium with carbon dioxide. The delta H for this is negative 393.5 kilojoules per mole. Which direction will the equilibrium shift if oxygen is added to the system? So let's have a look. We add oxygen, so it's this way, it's here, so it's going to go to the opposite side. So it's going to produce more CO2. So it's going to go towards the products. If the pressure is decreased, it's going to go towards the side with more moles. So here we've got 2 moles on that side, 1 mole on that side. So if we decrease the pressure, it's going to go towards the reactants. Now, if it's cooled down, so it's going to go towards the exothermic side of the reaction. And in this case, the forward reaction is the exothermic reaction. And so it's going to go towards the products. This one, nice and easy. 2 hydrogens plus oxygen gives us 2 waters. So which direction will the equilibrium shift if water is added to the system? So if we add water on this side, the equilibrium is going to shift to try and push to that side. Okay, so we're going to produce more hydrogen and oxygen. If the pressure is increased, so let's have a look. Firstly, we've got 3 moles on this side. We have 2 moles on this side. So if we increase the pressure, it's going to go to the side with fewer moles, so it'll go towards the products. And if the reaction vessel is heated up, so if it's heated up, it wants to go towards the endothermic side of the reaction. In this case, our forward reaction is exothermic, our reverse reaction is endothermic. And so it's going to be towards the reactants for that one. Okay. Another example, here we've got carbon and sulfur gives us carbon disulfide. If carbon is removed from the system, so if we take this out, it's going to move towards it. Okay, so it's going to try and produce more. So that's going to move towards the reactants. If the pressure is decreased, so again, when we're dealing with pressure, we count up the moles. This side there's 3 moles. This side there's just 1 mole. And so if we decrease the pressure, it's going to want to increase the pressure, and it increases it by increasing the number of moles. So it's going to go towards the left-hand side, so our reactants. And if the reaction vessel is heated up, or if it's heated up, it wants to go to the side that's endothermic, and we can see there because delta H is positive, the forward reaction is endothermic, and so this one is going towards the products. So, summary. This is going to be a little bit similar to your mini summary. Um, so if an equilibrium system is disturbed, then the system will move to minimize the change. Okay, hammer that into your head. That's the important part. So it does the opposite of whatever you do to it. If a chemical is added, then the equilibrium will move towards the side away from that chemical. So, if you add something to the left-hand side, it will push to the right. If you add something to the right-hand side, it will push to the left. If the pressure is increased, the equilibrium will move to decrease the pressure by moving to the side with the fewer moles. And if the temperature is increased, the equilibrium will move to the side that lowers the temperature. And again, all of these work in both directions. Okay. Now, what we're going to do after this lesson is we're going to do a prac. We're going to have a look at um, some of the actual examples of Le Chatelier's principle. Okay, we're going to look at some more cobalt reactions where we add one reagent and pushes to one side which has a certain color. Then we add a different reagent, it pushes back to the other side that has a different color again. We're also going to look at chromate dichromate, which is yellow and orange. That exists in an equilibrium system, and you can adjust it by using acids and bases. Uh, and I'm also going to do a demonstration of the nitrogen dioxide equilibrium, where nitrogen dioxide can exist as itself, but it's also in equilibrium with the dimer known as dinitrogen tetroxide. Okay, so um, 2NO2 is in equilibrium with N2O4. So that's the prac that we're going to do. So before we do that, though, have a go at these examples. Try to understand what's happening in the equilibrium systems. All right, thank you.